Hello, in this video we're going to look at the exponential family and how the multiple linear regression model fits into the exponential family. And really this is a precursor to, I'm creating a playlist called General Linear Models Regression. And there we just went through simple linear regression, now we're jumping into multiple linear regression. And one of the things that I want to show is that the least squares estimates are UMVUEs, uniformly minimum variance unbiased estimators. And to do that, the easiest way is to show that the linear regression model, or the multiple linear regression model fits into the exponential family. You find the sufficient statistics, and then you show that the least squares estimates are functions of those sufficient statistics. But anyway, I will leave more detail on that in a later video. But here we'll just jump right in. So here we're going to assume Y follows a linear relationship. So we have P predictors that we think are going to help us in predicting Y. And we think Y essentially follows this linear relationship with some error about that line in quotes. Here we're going to assume that the error term is IID normal 0 sigma squared, and we have a sample size of n. So one of these observations, yi, is IID normal with this mean, right? Because the expected values, these are constant. Expected value, this is 0. So this mean and the variance, these are constant, so they don't play a part. So it's the variance of this, which is sigma squared. Now, if we were to put this in the matrix notation, we'd say this vector y, which consists of y1, y2, y3, all the way to yn, is multivariate normal with this mean and this variance covariance matrix. Now, x beta, you can think of it as a data matrix, and the betas are a vector of the unknowns. And this right here, we get this relationship back. But it's so much easier to handle in the multivariate case. So f of y follows a multivariate normal distribution, and that's what this is, right? So there's the mean of it, and this is the variance covariance matrix, to the inverse. So that's the density. Now we kind of manipulate it a little bit. Now the inverse goes into both of those. This is a constant, so it becomes 1 over, and that's why it goes down to the denominator here. Inverse of the identity is just the identity, so we get these back. And then you multiply those. So you take the y times the y. Remember, don't forget the transpose. That's what this is. And we get y times this and this times y. And since they're scalar, you can kind of reverse them to get, and then you get 2 times this. That times that is this. And the reason we're doing that is because we're trying to factor it into something that makes it the exponential family. So then this is just a constant out front. This parameter, sigma squared, we want to take the log of it and then exponentiate it. So we get it back, but this goes into the model right here, right? Because the log, the n minus 2 comes out front, but that minus makes this minus. Everything else is the same. So this comes down. This is here. The 2 cancels with that 2. These are all, there's no y in it. It's all parameters. So that comes down to here and this to here. Now, this piece here is a function of just the parameters. And remember, the x's are considered fixed constants. So this is a function of the parameter space. And it's actually called the log partition in the exponential family, how you make it fit into that family. This is a function of the parameters times the data, y. Function of the parameter times the data. So these two are your sufficient statistics. This one and this one. Now we want to put it in canonical form. So what we do is we just generically say, call this eta 1 and this eta 2. And then we write this in terms of eta 1 and eta 2. So if we let eta 1 be this one here, And the reason I want to put that one first, I'm actually just going to switch those in what's down here. Eta 2 is this right here. So then this becomes what's called the canonical form. So this comes down the e to the, so this we just call an eta 1 and y, and this is eta 2 and y prime y. And then the log partition, you have to kind of manipulate it to make it a function of eta 1 and eta 2. And this generically is called a of eta, and this is a vector, so it's eta 1 and eta 2. And this is what's called the log partition. And so the cool thing about the log partition is if we start taking partial derivatives of it, then we can get the mean, the variance, the covariance, etc. of our sufficient statistics. Okay. Now to do that, these are matrices. So we're going to need matrix calculus. So in what follows, I use what's called numerator notation. And if I can do anything for the statistical community, that when you start taking derivatives of matrix, you either tell us that it's in numerator notation, denominator notation, or a mixed notation, right? And a good resource for that is the Wikipedia page on matrix calculus. I use numerator notation, and they go back and forth. And the reason I'm saying that is on some of my videos, I get someone that's adamant that my results are wrong because it's off by a transpose. And that depends upon which notation you use. Now I have 3 videos called the derivative of the determinant, derivative of the quadratic form, derivative of the trace, and the results what follow on the next page are all contained in these 3 videos. So now let's find the moment. So let's find the mean of our first sufficient statistic, which is this, and eta 1 was in front of that. So if we take the partial of our log partition with respect to eta 1, which is, and this is our log partition, then the derivative with respect to eta, well, that should say eta 1 right there, and then we get this piece down here. And then there's no eta 1 here, so it's constant and goes away. Now if we put in what we know for eta 1 and eta 2, we put these in and then cancel everything, we get x beta, which actually we know in the multiple linear regression setting, the mean of y is x beta, it's the function. So let's look at the mean of our second sufficient statistic, which is y prime y. That means take the partial derivative of a log partition with respect to eta 2, and this is our log partition. So this first piece up here goes to this, and then this one, it's an interest, so it's the log of the determinant, and ends up being this right here. Okay. Now what I do is in this, the -2, I actually bring out, so it raises it to the nth power, and then the log of a product is the sum of the logs, so that first one goes away because it's constant. Then I just take the log of the derivative of eta 2, and that's what this is. Now we replace what we know about all these etas. This one ends up going to here, this one is this, and then it simplifies. Actually, I switch it. I put this first, and then this simplifies to this. But the cool thing about this is, in the univariate case, if we were to say the expected value of y squared, we would say, oh, that's the variance plus the mean squared, right? So this is the equivalent multivariate case, right? So really, it's the variance. This is the variance plus the mean squared, right? So it's the equivalent. So now let's look at the variance of our first sufficient statistic, which is the variance of y bar, our vector. So that means take the second partial derivative with respect to eta 1 of the log partition. Now we already have the first derivative of our log partition, which is here, right? So now we just need to take the next derivative with respect to eta 1, and we get this. It comes out front. And we plug in what we know, which is this, and it becomes sigma squared I. And actually, when we set the problem up, that's what we said the variance of y was, sigma squared I. But anyway, it's just so cool that you can redrive it using the theory of exponential family. So here's a quick example. The least squares estimates of beta and sigma squared are functions of these sufficient statistics, right? So the least squares estimate is this in the multiple linear regression setting, which is a function of y, right? These are constants. Now the variance estimate is it's essentially the residual, sum of squares residual over some number that makes it unbiased, and it's n minus p plus 1. This is how many unknown beta parameters there are. And then I have a video in the playlist that shows that this can be written in quadratic form like this, and then when you multiply this in, it becomes this. And look, this is a function of our second sufficient statistic and our first sufficient statistic, right? Oh, H is the hat matrix here. So both of these are functions of the sufficient statistics, and therefore actually the beta hat and sigma squared hat are unbiased, and so they're UMVUEs. Now technically we have to show that they're complete, which they are because they're non-degenerate, parameter space, so they are complete, and that kind of shows that they are UMVUEs. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.